So in this tutorial, we're going to be looking at building a parser for our language that we've been making in all but the last tutorial using the parsing that we learnt in the last tutorial. Now, we're not going to use the parser that we wrote last week. The reason being because it's slow, but also because I can introduce you to some more things about Haskell if we use a library. So the library we're going to use, if I open the Cabal file, is attoparsec. Now, attoparsec works with either byte strings or text instead of Haskell strings. Now, Haskell strings are just linked lists of characters, and that's not the most efficient way to deal with a string. And so people have written two libraries, byte string, text, there's probably more, but those are the two main ones, for dealing with strings in a much more efficient way. They're implemented under the hood as C arrays. And that's because it makes very little sense for sort of indexing arrays of bytes using an ON algorithm. And given that we, rarely only ever go from front to back in a list, it's useful to have another form of string. And so attoparsec works on both of those. And I've opted to use text because it's slightly easier when it comes to text. Byte strings can hold any kind of arbitrary data in bytes. It's not geared up for strings. And there are kind of plugin libraries for strings. So I thought it would be simpler just to go from text. Good. You'll find that attoparsec is almost identical to the parser we made last week. It's a lot more efficient though. Let's just dive into the code. So cabal REPL. So I was having some problems earlier with this, but let's see. We have we have what I wrote in my second attempt to make this tutorial. So far what I'd done, instead of redoing it, is I'd imported data.attoparsec.text, and I have hidden take. And the reason why is because take is defined in both attoparsec and prelude. And we want to use the prelude take. I think we use it somewhere in our parser. The other thing is I've imported text, data.text. I've imported it, I've done a qualified import as T, and that means that anything in the data.text library, I have to stick a T dot at the front, and that's because there are absolutely loads of functions in data.text that interfere with the prelude. Good. And I'd only actually defined two functions and not very well. So this is the main parsing function. And if I come out of this, you'll see that parse fun is of type t.text to either string or expression. So that's going to parse our expressions. And then I also didn't really define, I set it to undefined, parse expression. Et, parse expression, which is of type parser expression. So the same type as the kind of parsers we were making last week. And I've opted to make it undefined. And the reason for that is because a really fantastic way of making sure that you haven't messed stuff up in Haskell is to kind of make sure that whatever you've written compiles so that you don't end up having to write huge, vast swathes of code of sort of interdependent functions and having written all of them fully, then see if your code builds. That's a good way of getting absolutely loads of compile errors. And we're using the parse only function from attoparsec. There's kind of three parsing functions in attoparsec. There's parse, feed, and parse only. Now, parse only consumes the whole of your text and either fails or outputs a string. Not a string, it outputs your sort of structured data, in our case, the expression type. There's also parse, and parse is almost the same, but it returns something of type result. Now, result can be in three different sort of forms. It's either done, in which case it gives you your structured data, or it fails, in which case there was a syntactic error somewhere in what it was parsing, or finally there's partial. Partial's interesting. Partial means nothing's gone wrong, but we clearly haven't got enough text to fully parse this. And then feed will take a partial result, and you can give it more text, and it will parse more. And that's really useful. So I use that a lot at work because I use attoparsec for what it's actually designed for, which is parsing TCP protocols very quickly. Because we should really be using Parsec as our library, but Parsec's a little bit more complicated, and I haven't used it at work. So we're doing Atto Parsec. And so what I have is I have a function at work that, I say parse from TCP socket and give it a TCP socket. And then it reads from the TCP socket. It parses that. And if it's partial, it then reads another 1024 bytes, because you can't just say read all from a socket in the low-level networking library in Haskell. You have to say how many bytes you want to read, and it will return at most that many bytes. So it's nice that there's a feed function, so you can sort of lazily, you don't have to have any kind of function that checks when we've got to the end. Instead, you can, have the parsing function constantly read from that TCP socket until it's done. So it's very cool, very cool. Okay. Yeah, so let's get parsing. First of all, we're not going to parse this in one function. That would be absolutely insane. You'll see that parsing functions are quite long. I'm also going to actually make a little shortcut. So in Atto Parsec, there's this lovely skip space parser, which just consumes a huge amount of space, white space that is. And it's quite a long function name, so I'm going to abbreviate it to SS. Good, so what should we start with? So numbers and booleans, they're both constants, so I think it's good to start with those constants. So parse const is going to be either decimal or true or false. We'll have capitals, true or false. Now this isn't all it takes. We have to tell it how to turn it into a number. So decimal is a parser of integers. So what I'm going to do is I'm going to use fmap to sort of get that integer into the number constructor. So if I go number and then fmap decimal, then that is a parser for numbers. Yes, I'm going to do it like this alignment-wise, I think. I think that's quite nice. Now, have I got... So I've got this overloaded strings thing. I think we've used it before. I can't remember. Maybe we haven't. Anyway, Haskell will always interpret what's in quotation marks as Haskell strings. But if we enable this language extension, it can interpret it as other forms of strings. So it could interpret it as text, it could interpret it as a byte string, but it doesn't stop there. So Atto Parsec actually can interpret that as this. So string is Atto Parsec's string parser. So it's going to parse the string true. But they've made it so that you can kind of drop that. And so true in quotation marks is a parser of the word true. And Haskell works out what sort of string from the type context. So because we've smidgened it in between these parser combinators, it knows that true in quotation marks is supposed to be a parser. But it's not helpful in this form. We need to have pure and then Boolean true and pure Boolean false. So, to reiterate, this fmaps the function number, which is the constructor, so it takes it in and returns an expression, with decimal. So decimal is of type parser int, so that's going to receive some text and return to us an int when it's used as a parser. So that gets us number int. So it's parsed that, and we can use that now. So we need to set in GHCI set x overloaded strings, and that is so that when we do this, here's a string, it can interpret that as text or t.text. So parse fun, and then we'll give it... Oh, hold on. I've forgotten to do something. So this expression, we can't keep it undefined. It's just going to equal parse const. Good. Good. So I think it will keep that. So parse fun. And then the text, if we give it a 10, it says, look, it's right, it's succeeded, and it's a number 10. If I go true, it's a Boolean true. If I go false, it's a Boolean false. So we're managing to parse our constants now. Good. So next, plus, minus, I'm actually going to save them. And the reason for that is because they start with expressions and are infix. And that causes a bit of problems when it comes to parsing. So I'm going to skip over them for now and go straight to if. Okay. So, parse if. And that is of type parser expression. Let's also just add these types. Parse const is of type parser expression. It just makes it clear that although parsers are functions, we kind of deal with them like they're single types, single things. Because if you think of this f map as acting on a function, it gets a bit confusing. So you think of decimal as a parser, not as a function. Okay, so parse if. So this one's fair enough. I'll probably do this in do form. I think that'll be slightly easier. So we have if, and then what we're going to do is skip some space. Then our condition is going to be parse expression, and then yeah, we'll skip some space afterwards as well. I'll try and do that at the end of every line to make that less confusing. Good. And then we have a then. And then we're going to pass another expression. So E1 is going to be parse expression. And then else. So you have to skip a lot of space in these languages. E2 is going to be parse expression. So that's quite simple, really. I've said, you know, we pass the word if in some space, then we have an expression as a condition, then it's a then we have our first expression if it's true, else, and then if it's false. So I could have used I could have done this in more of an applicative form. I guess I could have tried to you know, I could have used the oh, I haven't finished this yet. Return if, and then cond E1, E2. But what I was saying is I could have had my constructor if, and then I could have used the applicative function. There's nothing really like monadic that isn't applicative about this. And applicatives are, I hear, I don't know if it's true, but I think it's true. I hear they're more efficient when it comes to compiling. So what you can do is there's a language extension. I might have forgotten its name, but I think it's applicative do. And what that's going to do is that's going to, if it can, pass a do, some do, you know, if it can pass this or desugar it to applicative form, it will do that instead because that's more efficient. So let's have a look. Yep, we didn't make a mistake there. So we can modify our expression to not just pass constants, but to also pass our if condition. Pass if. Great. So now we can test it. Parse fun. and then we give it if true, then 1, else 0. And here we go. If Boolean true, number 1, number 0. Perfect. So it's all starting to come together now. Equals. Yeah, we can do... No, we're going to save equals because it starts with an expression. You know, it's expression equals another expression. Okay, so we're going to move on to a variable. Okay, so we're going to pass some string now. So what I'm going to do, thinking ahead, is I'm going to define a parser of an atom, and that is just some text. And so you'll see why in a second. So atom, so what we have is we have take while 1, I think. I think that's what it's called. I can have a look in the documentation. Take, take while 1. Yep, good. So take while 1 will continuously look through a list or through string while something is true. Now that would be take while. So the 1 means if it is going to return an empty list, then it will fail. So yeah, I'm just reading this. Apparently it's much more performant, about 100 times more performant than using many one any char. Who would have thought? Okay, so we need to give it a condition. So we'll say, so if we have our character as C, our condition is going to be C is not a space. So C is not a space. Okay, good. And now what we're going to do is we're going to have to change that a little bit. So we're going to go t dot unpack. And that's because our ident is defined somewhere as a string. And so to get from the t.text to a normal Haskell string, we use the unpack function in data.text. And this is quite long for just getting a string. So great. Let's do parse var next. So parse var is going to equal... Oh, what I'm also going to do is I'm going to say C is not a space, but also C is not one of these quotation mark. Good. Okay. So parse var is just an atom. So that's going to equal var. We fmap that with atom. Perfect. So let's extend our expression parser again. So we're going to have this one at the bottom. Because, of course, the atom parses anything that doesn't have a quotation mark or space in it. And our parsers do work in order. It tries this, then this, then this. And that means that it would parse if as a variable if we had it above if. I can show you that actually. So if I do this, save it, close it, you see it says var if, and that's not what we want. So we'll swap them back round, and you'll see the if is an if, but if I give it something like x, it will pass it as a var. Perfect. Okay. Let expressions. Lovely. So we'll do this as a do again, I think. Parse let equals do, and it's going to be let. So let me look at the type again. So we have a defen. Okay. So let, skip some space, then we'll say D is going to be parse defen. Now I've not defined that, so before I forget, we'll say that equals undefined. And then, okay, in, so, and then we have an expression. So our E is parse expression. Perfect. And then we return let DE. So let's see if that builds. Perfect. But we can't test it until we've defined parse defen. So if you remember, defen is it's kind of like an assignment, although it's not our sort of imperative programming assignment. It's not sort of an assignment of memory. It's more like a binding. But we're going to say either val and then a variable equals an expression or rec, depending on how we're going to use the environment. So let's do that right now. So this is val, and then we pass an ident, which is an atom. See, code reusability, we like it. I might do this in just applicative form. I don't know how clean it's going to be. So we have a val. Oh, and then we need an SS in there. And then we'll skip some space after it. Okay, so that passes val followed by atom and then some space. And then we have an equal sign. So I might put that in there as well. I think I'll do it as a char. I think char is more efficient for passing just a character. And then some more space skipping. Good. And then it equals an expression. So parse expression. So if I say that that is going to be, I think it's just val. Oh, and I need fmap and I need applicative. So fmap and apply. Oops, that's not fmap. Okay. And if I have a look, val. So you see it's val, ident, and expression. So val is a constructor that takes in a string and an expression and returns something of type defen. So here we have val. So that's a function that has sort of two inputs. So we fmap it over this parser, which passes the word val followed by some space and then an atom. And it sort of ignores all this, and then it passes some space and then the character equal sign and then some space, but it ignores all of this as well. But if any of this fails, the whole thing will fail. So that's going to give us an atom. Now, an atom is of type string, and so this together is of type functor. Our functor is a parser, so parser expression to defen. That's inside the parser. So we use the applicative combinator to get our expression. So hopefully that worked. Amazingly it did. And we're going to clone this line. What would be the quicker way of doing this? And we have rec, which is lovely because it's also 3 letters. Look at that. Good. So, yes. How shall we proceed? So there's a lot of duplication here. So I probably could have had you know, I could have probably had some kind of selector here instead, but it's fine. Let's see if that worked. Good. So let's add let, parse let to our top parser above var. Whilst let will be interpreted as a variable. Let's see if that works. So let val x equal true with a capital in if x then 1 else 0. And here we go, we have a let, and then we have val x is the boolean true. Great, so we have our definition sorted. And then we have our body, which is if the var x, number 1, else number 0. So this parser is going well. Lovely. So we've made it to if, let, var. So next we have lambda and then apply. So I'm probably not going to bother doing these ones. You can do them yourself, but I don't want this video to end up too long. And then of course I'll do the plus, minus, and equals. But let's do the lambda and let's do apply. Okay, good. So parse lam. Let's have a look. How are we going to do that? So lam is a list of idents and then an expression. Okay, so we will take the Haskell syntax on this, I think. So a lambda is, you know, backslash and then a variable list. Then we have an expression. Okay, so this shouldn't be too tough. So the first thing we're going to do is we're going to have the backslash. We have to escape it with a backslash. So backslash backslash is the character backslash. And then we shall parse our character list. Okay, so we're going to make a parser of just a list of space-separated atoms. So we'll call it parse atom list. And okay, so what we'll do is we're going to do this, I think. Yeah, okay. So, so what we're going to do is we're going to parse an atom and skip some space. No, yes, we will. So that's our first thing. And then we're going to have many one. So a list of one or more. Actually, I could just use many one. But that's not going to get the space separation. Okay. Yeah, no, I'm not going to do that. I'm just going to say many one. Apologies. Okay, so ins is just going to be many one atom, skip space. That's the wrong way. So remember how this works. Remember how this works, this many one. So many means keep on trying this parser and build a list out of everything it manages to parse until it fails. And many one is the same, but it will fail if the list is empty. So that's ins. So that's our inputs. And then we pass an arrow. And we'll skip some space. And then pass expression. And then we return lam ins our expression. I'm going to change that to a p, I think. Okay. So let's try that out. Good. It succeeded in parsing. And we shall pass our lambda up in here. And we'll try it out. Parse lam. Lovely. So, moment of truth. So, lambda x to x. So the identity. Ooh. Ah. I need to backslash it twice. There you go. Oh, no. So what's going on here? So it thinks it's a variable. So I have a feeling it's not liking my inputs of this. Let me try. If I just do it with an exclamation mark, let's double check that it's not the escaping error. No, it's not escaping. So why is it skipping that line? Okay, let's do it this way. We'll build this up from the beginning. Okay, so the exclamation mark is fine. Next, we have atoms. It's going to be many1 atom SS, and you'll stick atoms in here. Ah, it passes far too far. Okay, so do you remember our atom function? We also need to add that C is not equal to dash. But I don't like doing that because I feel like we should be able to have dashes in names. So yes. So what the problem was it was passing far too far. The many atoms was passing too far, and it was passing our this symbol as a variable, and it meant that it never got to expression passing. But I'm going to leave that like that for now. I need to give it the right type, so that will fix it. So if I carry on as I did before, so we pass our arrow, and then we skip some space, and then we pass an expression to expr, and then we change this to expr. So this should work. Yeah. Okay, we're going to leave it like that for now. We have, it doesn't have to be good. This is a tutorial. You can use a different atom parser. You don't have to use the take while, which only looks at individual characters. You can use regular expressions. What normally happens is you'd first go through and do lexical analysis. So you turn all of these strings into symbols anyway. But this is a tutorial, you know. So we're going to have the imperfect addition of that dash. Good. Okay, so we have lambda parsing. So all we need now is to apply it. So application is going to be... how are we going to do application? So what is application? Application is an expression. We're not going to do application yet because it starts with an expression. Okay. So let's go back and let's look at this plus, minus, equals, and apply. And maybe, I think that was it. Or equal. Yeah, we said that. Because they all start with expressions. So the problem with that, I will show you. So let's do sort of the naive parse add. Okay, and that would be plus, and then it would be something like parse expression I'm not going to bother with the space. Plus, and then parse expression, and that would have to be the other way around. Okay, that's the naive version of plus. We say it's an expression followed by a plus followed by an expression. And if we were using a bottom-up parsing library like Alex, which is in Haskell, we could actually write this, and it's clever enough to work out how to do this. Yeah. The problem is, this is recursive. We're in parse expression, we go and call parse expression, and we loop indefinitely. So I'll show you what this does, just to prove that this is a bad idea. So if I go parse add, then if we try and parse anything, it loops forever. Okay? So we're going to not do that. We're going to go and we're going to work this out. So the way we tend to get around this, I'm also going to change it to plus so I don't confuse myself. The way we tend to work around this is we tend to do a parser that is, it kind of does sort of, we parse a term plus an expression or a term. Okay? And then we say a term is equal to either, well, in this case, because we have multiplication, we'd say that a term or parse term equals something along the lines of term 2 multiplied by an expression, or it is a term 3. Oh no, it's a, yes, or it is a term 2, I mean. And then we say parse term 2 is equal to an expression, like that. I'm pretty sure that's how we do it. Not quite. So that would be a term as well. And then we tend to say something like this. And that allows you to do things like 1 plus 2 plus 3, or 4, 3. But it doesn't, but you'd have to put functions in brackets and whatnot. But you can see there's nothing recursive about this because the first time we hit expression, it's going to loop. Now, it limits us in some way because we can't have an expression. I can't say something like x plus 12. But I can say 12 plus x. So a little bit strange. The alternative is to add the parts of expression here that we don't feel needs bracketing. So yeah, that's what we're going to do. Okay. Sorry for the brain splurge. But this is, So let's comment this out, but we're going to use this as kind of a model of what we're going to do. Good. So parse plus do. So what this is going to be is we're going to say t is going to be parse term, which does not yet exist. So parse term is undefined. Okay. Oh, and we're going to skip some space after it. Then we're going to say we're going to pass the character plus. Okay. Now we also could do this actually. Actually, do we have minus? Yes, we have minus. So because plus and minus are both sort of on the same level of binding strength, we should probably do them both in one. So what we can do is I'll have con for constructor. Okay. So if it passes a char, yep, then what we'll do is we'll say pure plus. Okay. So con is going to equal plus if we hit a char. Now what I'll also do is I'll say or, and I'm going to put this all, I'm going to take that out of brackets and put this in brackets, this whole thing. And if we have a minus sign, then it's going to be pure minus. Okay. And then I'm going to skip some space. And then what I'll do is I'll pass the expression. And then we return con t e. Now I have no idea if that worked out well for me. That's a bit gnarly. Let's check. No. Variable not in scope, parse add. Ah. We renamed it to plus. There we go. So there was actually nothing wrong with that parser definition. Good. Okay. So that passes plus or minus. So I'm going to change that to PM for plus minus. Now we can't call it because we'll hit this undefined parse term. But we can do that anyway. It will give us a nice error. So 10 plus 2. It just passes the number. And that's because the addition fails. But that's fine. Let's move on to parse term now. So term, what will term deal with? We'll say that term deals with multiplication. Okay, because we want multiplication to bind stronger than plus or minus. And we'll do another one for equals. Okay. And remember, we need to have that kind of here. We have that term that goes past it. So we'll say term, parse term, sorry. Or do. Whether that will still work. Is that still syntactically? No, whoops. What am I doing? Yep, okay, good. So, parse term equals parse factor or do. Okay? And what we say is we say that f equals parse factor. Sorry, I've done this the wrong way around. Because it does that first. We'll never get past that. So I'm going to have that as a prime. Okay? And then I'm going to say parse PM equals parse PM prime or parse term. Okay? And parse term equals parse term prime or parse factor. The order matters. Okay, so we pass a factor into f. Don't forget to skip space. we're then going to have the char multiply, followed by skipping some space. And then we're going to pass a term again. So t is pass term, and then yes, that's it. Sorry. And then we return mult. I think it's mult. Oh, look. We don't actually have multiplication after all that. Oh. Well, ignore that. I didn't even realise we didn't have multiplication in this language. Oh, dear. Okay, change of plan. Equals equals. And we have return equals and then f and t. Okay. And here, that'll be fine. Parse factor is going to be this one's easy enough. So char open brackets parse expression char close brackets. Let me add in the necessary, oh, wrong place. Add in the necessary or and now we can say basically any of these that doesn't have parser as its first term. So what I'm going to do is I'm going to copy all of this and I'm going to say that this is parse expression prime, and that's just the ones that aren't that don't start with an expression in infix form. So those are fine, but it's not going to have PM. And then of course we can remove this and we can say that this is I hope the order doesn't matter so much. No. Parse expression prime. Okay. And so all the way down here, or parse expression prime. So maybe, 146. Oh, I keep on doing this. That shouldn't even be there. Oh, that's not a character. That is a string. My bad. Okay, so we have our parser now. Shall we see if it works? There we go. We can parse a number plus a number. Really cool. So we finally need application, which I haven't done. So where am I going to smidgen that one in? Okay. Cool. Okay. So it's an expression followed by a list of expressions, if I'm right. And that's the last thing we're going to do. So expression followed by a list of expressions. We might have that binding stronger than these. Or should we have it just different? Ooh, application is a tough one. Or we can just have some different syntax for it. I haven't really thought of this yet. I still don't plan these tutorials. Okay. Nah. Instead, let's just make up some funky syntax for application. Okay. The way I'm going to do application, I have decided, is parse application equals do. I'm going to steal some syntax from, weirdly, the spec files when you're building RPM packages. So it's going to be like the expression that is the function, followed by a colon, followed by our input. That is going to be how we're going to do. I don't know why, but I think it looks quite cool. Okay, so we're going to start off with the percentage sign followed by the open curly brackets. And then we won't have any space there. So we're going to pass an expression. Okay, and that is going to be our function. Then, without any space, we're going to have our colon, and then we might skip some space here. And then what we're going to do is we're going to have pass many expressions that are separated by spaces. So that's fine. So ins is going to equal many one. No, it can be empty. So many parse expression followed by space. And then we're going to return apply f and ins. And then I'm just going to have this aligned. Good. Okay. Oh, operator precedence. No, what have I done? Couldn't match actual type list expression with list in. That's because I've got this the wrong way round. Good. Okay, let's add that to here. Is it just parse app? What did I call it? Yep. Okay. Okay, so I've done some debugging. It could have been that. I don't really know, but it's kind of just started working. So I thought I'd show you, prove it works. Let rec fib, the classic Fibonacci function. So fib is a lambda, and it's going to map n to if n equals 0, then 0, else if n equals 1, then 1, else, then we do a function call. Fib of n minus 1 plus fib of n minus 2. In, we actually need to call it now, fib of, I don't know, 1 gives us a 1, 2 gives us a 2, 3 gives us a 2, 1, 1, 2, good. We can just keep on going. And you see that it is correctly calculating the Fibonacci sequence. And I think that's quite cool. We've made an interpreter from nothing, just in Haskell. Okay, fantastic. So we're going to move away from interpreters now. We're done. And yeah, next week we're going to go into language extensions, and after that we're going to go into sort of a much less pernickety topic, and that is making web services in Haskell, a bit more real-world Haskell for you. But I hope you've enjoyed the interpreter series. I've enjoyed making it, and hopefully I'll see you next week.